Alright, we're back. This is 5 and 6, Chapter 5 and 6 review, problem number 8. And it gives us this picture, and it says we're looking at this graph, y equals secant theta tangent theta. And we're also looking at the parameters y equals root 2 on the top. And on the edge, we're limiting by x equals negative pi fourths. And so it's important to look at this and realize the area that we're trying to find is the area enclosed and circled by these functions, all right? I personally looked at this and I thought, I'm going to integrate with respect to x, because I think we can do it with respect to x probably easier than we could with respect to y. That's purely intuition. You could probably figure out how to do it with respect to y. It probably wouldn't be much different, but I just have a bias towards integrating with respect to x. So I draw my rectangle. I'm going to be adding infinitely many rectangles that are encircled by this whole parameter. So I take a look at it and I find that my small chunk of area for each rectangle is equal to the height of the rectangle times the width of the rectangle. And of course the width is going to be the infinitesimal x, the height is going to be h, and the area, when we take dx times h, is going to be our small infinitesimal chunk of area. So, first thing to figure out is what is height? Well, height is going to be top minus bottom. And for every point from here over, you'll notice that top minus bottom is equal to y1 minus y2. y1 being the line y equals root 2, and y2 being the line y2 equals secant theta tangent theta. Oh, and I'm so sorry, this is silly. They're doing it in terms of theta. I said I was going to integrate in terms of x. Let's change that. We're going to integrate in terms of theta. And so in this case, these x's that I have written here are also thetas. Now, if you did it with x, you'd get the same answer, but we're just going to try to stick with what they want. So everything's in terms of theta. Theta in this direction, y in that direction. And so height is going to be root 2 minus secant theta tangent theta, because for every given point, there's a rectangle that works using that formula. So height is equal to y1 minus y2. I just labeled them y1 and y2. You could label them differently, which is root 2 minus secant theta tangent theta. Alright, so now that we found the height, we know that dA, our infinitesimal area, is equal to our height, which is root 2 minus secant theta tangent theta, and we're multiplying that by the infinitesimal width of each rectangle dx. Alright, now what I'm going to do is I'm going to take the integral of both sides, and the integral of 1 with respect to dA is a. So area equals, and then we're going to have to figure out what our boundaries are now. So we're integrating with respect to x. We're going from here all the way to here. And the boundaries that appear naturally are, we're going from negative pi fourths to theta equals pi fourths. So we're integrating with respect to theta, and our rectangles start at negative pi fourths and end at positive pi fourths for theta. So we're going from negative pi fourths to positive pi fourths. And look, I did it again. I put dx. I meant the infinitesimal width d theta. I'm so used to dealing with theta in terms of angle measure and not actual linear distance, so it's throwing me off a little bit. So we know our parameters, we know our boundaries, and we know what height times width equals. So now we have this integral set up, and this will give us the answer. Now at this point you could type it in the Symbolab or integral calculator, and it would give you an answer, but I want to walk through this integral. But in order to do that, I'm going to need to clear some board room. So hopefully this drawing was useful to you. I find that drawing graphs really helps me out. I'm a very visual person. So alright, what's next? We'll write it up here as we have it written down there. We're integrating from negative pi fourths to pi fourths for the 2 minus secant theta tangent theta with respect to theta. That's our width. Alright, so now I'm going to get rid of everything and make even more room. So here's how I would approach this integral. The first thing I would do is I would split it. Using linearity, I would split it into two integrals. They will both have the same boundaries, but one of them is just going to be root 2 d theta, and then I'm going to subtract the integral from negative pi fourths to pi fourths for secant theta tangent theta d theta. So using linearity, I can split them up. Right off the bat, we know that the integral of root 2 with respect to theta is root 2 theta. So root 2 theta, we are evaluating this from negative pi fourths to pi fourths. Those are our boundaries. And a equals over on this side. Now this one's a little trickier, but it's actually not bad if you have your cheat sheet of derivatives in front of you. Personally, I have this one memorized. The derivative of secant theta with respect to theta is secant theta tangent theta. So, in other words, if the derivative with respect to theta of secant theta equals secant theta tangent theta, then we can do this whole process backwards, right? Because integration is an antiderivative. So we can also take the derivative of both sides. That'll get rid of, we can take the integral of both sides. That'll get rid of the derivative over here. Those will cancel. And what you'll end up with is the integral of secant theta tangent theta equals secant. So we have secant theta tangent theta up here, and the integral of that equals secant. So now we have secant theta is our integral, and we're evaluating it from negative pi fourths to pi fourths. And then we're going to subtract this evaluation, right? There's a subtraction sign here. And this will give us our total area. So let's evaluate each of these separately. The first one, we're going to have root 2 multiplied by pi fourths for our first evaluation, then subtracting. When we plug in negative pi fourths, we end up with minus root 2 pi fourths. Alright, and so we can combine these. A minus, double negative is a positive, so we're actually turning this into root 2 to root 2 pi over 4. The 2 and the 4 cancel to leave a 2 in the denominator. So this side's evaluated right here. Alright, now let's go ahead and evaluate this side. It'll probably take a little more room. The first thing I'm going to do is I'm going to go ahead and say secant is equal to 1 over cosine theta, because I know my unit circle for cosine. I do not know my unit circle for secant. So, but the nice thing is we can always change one into the other. And so secant is equal to 1 over cosine. So now we're evaluating, on this side we're subtracting 1 over cosine of pi fourths minus 1 over cosine of minus pi fourths. And cosine of pi fourths is root 2 over 2. Root 2 over 2. And cosine of negative pi fourths, let me think here. Negative pi fourths would be down here, and cosine is the x. So it appears that it would still just be root 2 over 2. Let me check that real quick. So pi over 4 minus, take the cosine of it in radians. It's actually, it's positive root 2 over 2. So we're also getting a positive root 2 over 2 here. Root 2 over 2. And interestingly enough, it appears that these two expressions are the same. And so it seems like they're going to cancel. And so these are going to cancel and go to 0. Oddly enough, I really did not expect that. And then you could plug this in as the answer and it would be right. But the way the computer wants it is to make it as simple as possible. And to do that, you can times, let's see here, you can times both the top and the bottom by root 2. Root 2 over root 2, we're not changing it, we're just timing it by root 2. And root 2 times root 2 is 2. We still have the pi tacked on. And then 2 times root 2 in the denominator. and the 2's cancel up to 1, and what we're left with is area equals pi over root 2. So I hope this video was helpful, and I'll see you next time.